Hello everyone. Today we're going to start talking about perms and coms, and more specifically we're going to talk about perms or permutations. So permutations and combinations are called enumeration in math or counting. So counting can be very difficult, and it is really how many different ways elements in a certain set can be arranged in various situations. And really, we're just going to be making arrangements out of different elements of set or different things, as we'll see. So let us begin by discussing the fundamental counting principle. Suppose that there are two decisions or tasks to be made. The first decision or task has A possible outcomes, and the second decision or task has B possible outcomes. Then the number of ways that two decisions can be made are A times B. And the reason for that is here I'm going to let, if I know that the first task has A possible outcomes, and I'm just going to simply multiply that by the number of ways that B has outcomes. Pardon me. Now, this is just for two. However, this can be generalized for n decisions. So for n decisions, well, how many ways can the first task be done times how many ways the second task can be done, third task, fourth task, in which each letter represents the number of possible outcomes for each task. And you just simply multiply it by the number of options available to you in each task. That is the fundamental counting principle. So let's do an example of the fundamental counting principle. CMMC is having a 100-meter race in which there are three competitors: April, Billy, and Cora. Identify the number of different orders of the racers that can cross the finish line. All right, so I'm going to do what is known as a tree diagram. And here is my first task or decision. So let this dot represent who comes in first. There are three possible outcomes: April, Billy, or Cora. Now, these represent first place. Now, I'm going to draw branches of this tree diagram to represent who can get in second place. Well, if April gets first, well, Billy or Cora can get second. If Billy comes in second or first, then April can come in first or Cora. Now, if Cora comes in first, then it's up to April or Billy to come in second. So now what we see is that if April's first and Billy's second, then Cora must be third. If April's first, Cora's second, then Billy must come in second. If Billy's first, April's second, then Cora. And we can continue this on simply by noting who is yet to finish. And how many different arrangements can be made? Well, we could just simply write down these letter acronyms to help us out. And this is not using the fundamental counting principle, but it's using a tree diagram. So when there's three racers, it looks like there's 6 possible orders. So now let us go on to the fundamental counting principle. Now, the fundamental counting principle is going to answer the same question, just in a very different way. How many decisions are there to be made? Well, for 3, correct? And we have April, Billy, and Cora. So who comes in? This first block represents who comes in first, second, and third in our race. So how many decisions or how many outcomes are possible for first place? There's going to be 3. So given, now I'm just going to say, let us assume that April came in first. Well, how many decisions are there for the person who came in second? Well, now there's only 2 remaining people. How many people came in third? Well, after you have first and second, third place, there's only 1 option left. And what we get is that there's 6 possible orders, exactly the same as the tree. Now, look at the amount of work that has to be done for method 2. So, and it's far easier to think about it in method 2, so the fundamental counting principle. All right. Dora is looking at her closet, in which she has 4 shirts and 3 pairs of pants. Identify the number of outfits she is able to make. So here, I guess there's 2 decisions I have to make. One of them has to be which shirts I'm going to wear. And the second is which pair of pants I'm going to choose. And I could make a tree, or I could use the fundamental counting principle like I am. So there are 4 options for the amount of shirts I'm going to wear, times 3 options for the amount of pants I'm going to wear. So that gives me 12 combination, and I'm going to call this combination, sorry, wrong word. This arrangements is going to be 12 outcomes, right? So there's 12 different arrangements. And actually combinations is the correct word, but as you'll notice as we go on, I have to be careful where I say permutations and combinations. But right now we're just talking about the fundamental counting principle. Yeah, next question. This is a great question. Quite hard though. Maybe? There are 5 boys and 2 girls in a class. All students are seated in a horizontal row. How many arrangements are possible if a boy must sit on the end? Oh, sorry. How many arrangements are possible if a boy must sit on each end of the row? So there has to be boy on either end. So what am I going to do is I'm going to say there's a total of 7 people here, and they're all going to be seated in a horizontal row. So I am actually going to just simply put spaces out for 7. 1, 2, 3, 4, 5, 6, and 7. So right now I have 5 boys and 2 girls. So there has to be a boy here and a boy here. Now this is known as a constraint. If they are giving you an order of what must be obeyed, it's called a constraint. And you generally have to deal with constraints first. So boys, I'm going to mark up in blue. Boy, boy. So right now, I am going to say, I'm going to put a boy right here. There are 5 possible choices in which I'm going to put a boy there. Now, once I put one boy there, there's only 4 boys remaining. So I have to put another boy at the other end. So here, I have 5 boys. And now I'm just going to say I have 2 girls in the class. To help me illustrate this, I'm just going to arbitrarily just take any 2 people. Boom, boom. I have dealt with all the constraints. Now I can place everybody in their seats. So I'm going to go with this seat here. It doesn't matter which seat. How many possible decisions or how many possible choices are there for this decision? Well, there's 5 remaining people, so there's 5. And in the next seat, well, there's 4 possible people. And in the next seat, there's 3 possible people. And in the next seat, there's 2 left. And we arrive when there's only 1 person left. And there we have it. So 5 times, there are 5 times 5 times 4 times 3 times 2 times 1 times 4 possible arrangements. So I'll just quickly do that on my calculator. I encourage you to do the same. And I get 2,400 possible different arrangements. Now, so 25 times 4 times 3 times 2 times 4. Yep, 2,400. Fair enough. So again, I had a constraint, so I dealt with that first. Let's go for B. There are 5 boys and 2 girls in the class. Same situation. All students are to be seated in a horizontal row. How many possible arrangements if there are no constraints or restrictions? So what I know now, it doesn't matter. So, but I have 7 people to put in chairs. I'm going to pick, there's 7 possible options to go in the first chair. 6 in the second chair. 5 in the third. 4 in the fourth. 3 in the fifth. 2 in the sixth. And last, there's just 1 person to go down in the 7th. So this is really kind of fundamental here in math, and it is called factorial. And we'll see. So this type of arrangement, 7 times 6 times 5 times 4 times 3 times 2 times 1, is called factorial. And if you do that in your calculator, it'll be 5,040.